This is Module 9, Fatty Acid Metabolism. In this video 9-3, Catabolism of Fatty Acids, I'm going to talk about the pathways involved in beta oxidation of fatty acids, which helps to oxidize heavily reduced fatty acid molecules for the production of ATP. Fatty acids have to be activated and transported to the mitochondria for beta oxidation. And so the site of beta oxidation is the mitochondria. And many different tissues in the body can do beta oxidation. So fatty acid oxidation occurs in the cytosol. So when fatty acids are absorbed by the cell, they have to be activated by binding to a coenzyme A molecule. Remember, fatty acids don't represent it's not a high energy molecule. It is not unstable. It's a very stable hydrocarbon. And so in order for fatty acids to go through and be committed to beta oxidation, we have to destabilize that molecule so that it's thermodynamically favorable. So that instead of having this very stable molecule be oxidized, which is not as thermodynamically favorable as oxidizing a highly unstable molecule. And so Acyl-CoA synthetase will take a molecule of ATP and a coenzyme A and bind it to a fatty acid. And so this is an ATP-dependent process. Now, Acyl-CoA, so fatty acid molecules linked to a coenzyme A, cannot directly enter the mitochondria. And so this is happening in the cytosol that will activate it, destabilize the molecule, and make it ready for entry into the pathway. But it needs to get into the mitochondrial matrix where all the beta oxidation enzymes are. And so this means we have to transport Acyl-CoA across the membrane. But like as I just mentioned, this is a really big fat molecule now attached to a really unstable coenzyme. And so we have to find a way to transport it across and then reattach the coenzyme. And so a fatty acyl group of an activated fatty acid, so that's the fatty acyl group, is transferred to a molecule of carnitine. Carnitine acyl will enter into the mitochondrial matrix through a transporter protein embedded within the inner mitochondrial membrane. And so also the outer mitochondrial membrane. And so the carnitine will bind to this carrier protein very specifically. And so this protein only allows for carnitine-bound acyl groups to transport across into the matrix. On the other side, a second enzyme, which is similar to the first one, so these are transferase enzymes, will transfer the carnitine, pull it off of the acyl group, and then attach the coenzyme again. And so we started with an activated fatty acid and then had to sort of swap out the coenzyme for carnitine to allow for transport. Now we're inside the matrix, and so we reattach that coenzyme. Okay, so beta oxidation is the process of oxidizing an activated fatty acid into acetyl-CoA. And so we have to change this acyl-CoA into acetyl-CoA. This happens in the mitochondria. Acetyl-CoA, if you'll recall, is one of the two starting materials for the citric acid cycle. And so fatty acid energy production can be funneled into the middle of central metabolism. It begins its path of oxidation at the citric acid cycle point, skipping over the glycolysis point. And so you might think, well, if it's skipping the first stage of central metabolism, why doesn't it generate less energy? It's because fatty acids are very, very long chains of hydrocarbons. And so you can generate more energy because it's a more reduced molecule. It has more hydrogens to donate to NADs and FADs. So I'll talk about that in a second. The production of acetyl-CoA using acyl-CoA as a starting material will produce one FADH2 molecule and one NADH molecule, which feeds the electron transport chain. And so beta oxidation transforms fatty acyl-CoA into acetyl-CoA, but also generates reduced electron carriers that can be funneled into the electron transport chain. One round of beta oxidation. So one round of beta oxidation is pulling off 2 carbons from a fatty acid chain and attaching it to a coenzyme. And so that's one round of beta oxidation. One round of beta oxidation generates one molecule of FADH2, one molecule of NADH, and one molecule of acetyl-CoA. Acetyl-CoA via the citric acid cycle generates 3 more NADHs, 1 more FADH2, and 1 more GTP. And so if you funnel all of those reduced electron carriers into the electron transport chain and use oxidative phosphorylation to make ATP, you can generate 14 ATP molecules by oxidizing just 2 of the carbons from a fatty acid chain. And so one round of beta oxidation, is responsible for generating 14 ATPs. But this first round, each round of beta oxidation, will shorten a fatty acid chain only by 2 carbons. And so if you have a 16 fatty acid chain, that means you can do beta oxidation 8 times. Or I guess 7 times. And then the last cleavage reaction generates a 2-molecule carbon. And so here we have a 16 fatty acid chain. We can do beta oxidation 1, 2, 3, 4, 5, 6, 7 times and generate 1, 2, 3, 4, 5, 6, 7, 8 molecules of acetyl-CoA. So that changes all of this over here. And so we generate 8 molecules of acetyl-CoA and generate 7 FADH2 and 7 NADH if you're going to completely oxidize a 16 carbon fatty acid chain. And so 7 rounds of beta oxidation means, again, we generate 8 acetyl-CoAs, 7 FADH2s, and 7 NADH. Through the process of oxidative phosphorylation, we generate all this ATP through the production of reduced electron carriers, minus 2 ATP for the activation of the fatty acid at the very beginning, generating 106 ATP molecules for a single molecule of fatty acid. So this is why beta oxidation of fatty acids is more energetically productive than oxidizing a single molecule of glucose. Now, what if we have an odd chain fatty acid? We don't like to waste, right? The body doesn't like to waste. And so if you have an odd chain fatty acid, the very last stage of beta oxidation will generate an acetyl-CoA, but also a 3-carbon molecule. And so what happens to that 3-carbon molecule at the end? We can't do another round of beta oxidation. And so we take this odd chain, so we have acetyl-CoAs, which are all being funneled into the citric acid cycle, and then 1 molecule of propanyl-CoA. This is what's left over after you do beta oxidation of an odd chain fatty acid all the way to the end. And so this propanyl-CoA can, through 3 enzymatic steps, be converted into succinyl-CoA, which can be used to regenerate citric acid cycle intermediates. And so you might not have even noticed this last time when I was talking about the citric acid cycle. This probably looks familiar to you, where I was talking about the amphibolic nature of the citric acid cycle, where the citric acid cycle can be used to build things like fatty acids, cholesterol, and glucose, but the oxidation of other molecules can replenish citric acid cycle intermediates. And one of those is an odd chain fatty acid. So odd chain fatty acids can be used to regenerate succinyl-CoA in the citric acid cycle. So even an odd chain fatty acid with this weird leftover piece can be recycled and reused. Beta oxidation is regulated by energy state by the same molecule or the same hormones that regulate glucose metabolism and F26BP. So remember, the presence of glucagon will reduce amounts of F26BP, which will push flux towards gluconeogenesis. The presence of insulin will increase flux through glycolysis by producing F26BP and increasing PFK1, and at the same time decreasing FBPase1. So this is your committed step of glycolysis. So glucagon does all these things to glycolysis and glucose metabolism. However, glucagon also stimulates the activity of hormone-sensitive lipases. Remember in the first video when I talked about lipases, glucagon is one of the hormones that activates them. So epinephrine or glucagon can bind to receptors on the outside of adipose tissue. This will result in activation of a kinase, which will phosphorylate your hormone-sensitive lipases, which will then bind to tags in the fatty acid storage and produce free fatty acids. And so glucagon stimulates hormone-sensitive lipases, which will generate free fatty acids, which will increase beta oxidation through substrate availability, right? More fatty acids, more beta oxidation. And so here's a summary of fatty acid metabolism. Tags can be broken down into fatty acids. They can also be built into tags depending on where we are in the body. Fatty acids can be used to build membrane lipids, but they can also be oxidized via beta oxidation to produce acetyl-CoA. This process of beta oxidation will generate some reduced electron carriers, but the far amount of the energy produced through oxidation of fatty acids comes through the production of many molecules of acetyl-CoA, which can be funneled through the citric acid cycle to reduce even more electron carriers to make ATP. If acetyl-CoA is building up because the citric acid cycle has slowed down, acetyl-CoA can be transformed into ketone bodies, which can then be exported and used by some organs as a source of energy when the citric acid cycle is slowed down. So if this is happening, if citric acid cycle is slow, that means we're in a starvation state. And so acetyl-CoA is turned into ketone bodies, which can be used as a source of energy during starvation. Acetyl-CoA can also be used to build cholesterol. When metabolic fuels are abundant, however, lots of ATP, the products of carbohydrate and amino acid catabolism are directed towards fatty acid synthesis. And so we have enough ATP. And so if we have excess fatty acids, we will use those fatty acids and store them or use them to build other things. So if we have a lot of ATP, we're going to build fatty acids. Not a lot of ATP means we're going to use fatty acids for energy.